Now let's move on to question number 8.52 from the book by B.R. and Johnston on vector mechanics statics. Now in this question, it is a wedge type problem on an inclined plane. Multiple wedges are there. Now first of all, this whole assembly is mounted on a 20-degree inclined plane. Moreover, there are two 8-degree wedges and there is a 530 Newton block. Now in this question, it is being asked that two 8-degree wedges of negligible weight are used to move and position a 530 Newton block, knowing that the coefficient of static friction is 0.4 everywhere. Determine the magnitude of force P required for which the motion of the block is impending. Now, first of all, we take some important points from the question. It says that we want the force of P where the motion of the block is impending. This means that we want the value of P at the critical equilibrium case. Okay. So now I have shown a little difference between these blocks. So of course you can, in the actual diagram it is not there. I have shown it for clarity. So it is a multiple wedge on an inclined plane friction problem. So this type of problem may get a bit tricky. If you get involved too much, you can forget the forces, because there will be a lot of forces and a lot of friction forces will be acting, because it is given that the coefficient of static friction is 0.4 at all surfaces of contact. For example, this and all the surfaces of contact. So we have to be very careful about what we are going to do. Now first of all, let us start with this block. Let me call this as A, this as B and this as C. So what I am going to do is, number one, draw this block A, FBD of this block A. Okay, so this is a 530 Newton block A. Let us suppose that this surface, the bottom surface, applies a normal reaction here. Let me call it as N3, and the friction. Now the direction of friction becomes very important, because if you go wrong about the direction of friction, even after applying all the concepts you will get the wrong answer. Now here the motion of the block A is impending. So what is happening is the P is pushing it downward. The motion of block A will, if this P is brought down, block A will move up the plane. This means the friction force will be acting down the plane. Yeah. And this block B will be offering some normal force, that is N2. And again, this block B has the tendency to move down. Okay, so when block B is moving down and A is at rest, so the friction will want the relative motion to stop. That is, the friction will want A to be dragged down along with B, so that there is no relative motion between A and B. So therefore we can say, right, so these are the only forces which are acting. So what we are going to do, just write two equations, sigma fx is equal to 0 and sigma fy is equal to 0. In doing this, we are taking our coordinate system. Let's say I take coordinate system as this. Okay, so now let me write the equations. Number one, there should be no net force along this direction. Okay, so but here I observe that most of the forces are acting at an angle 20 degree. Okay, this. So why not I just tilt this coordinate system? Otherwise all these forces will require sine and cos components. Let me just tilt this whole coordinate system by 20 degree, so that this is my new coordinate system, say x dash y dash. Okay, by doing so we just have to apply the sine and cos component of the 530 Newton force now, not all these four things. Okay, so that's just a way of simplifying. Of course you can move with this also, there is no problem with it, absolutely no problem with it. So now we use sigma fx dash is equal to 0, okay, along this axis. So what is happening is N2 should equal 530 sine 20 plus mu1 3. So this is my first equation, and I have got it by sigma fx dash is 0. Now sigma fy dash is 0. I have to apply that condition also. That will give me n3 equals 530 cos 20 plus mu n2. So this is the second equation I have got, and this by sigma fy dash is 0. Okay. Now the analysis for this block is done. What we are going to do, we just move to block B. So let me draw a neat diagram of block B here. Here. So just suppose that force N1 is acting here. Now this N1 is due to this block C. Okay. Now again we have to ascertain the direction of friction which is acting. So, and one more thing to remember, this block is given to be massless, so there will be no mass. Had there been some mass, we would have incorporated that also, so it's just not a big deal. So just let's see what will be the direction of friction. This block is being dragged down, so there will be relative motion between these two blocks, but the block C will want this block to be at rest, therefore C will exert a friction force upwards. Okay. Likewise, this will exert a downward force mu n1 on C because it wants C to be dragged downward. So this just action reaction force, so the same thing we have done here. Now a force P is acting. This is what we are going to find out. And N2 action reaction forces. Now here just notice that N2 was acting here on this block, so here on this block action reaction forces, Newton's third law. And again what I was emphasizing earlier, here the same block B was trying to pull down the block A, but the block A will trying to keep this block B at rest by pushing it by a force mu n2, by a friction force mu n2. So all depends on the tendency of the objects, so tendency of the friction to avoid relative motion. Okay. Now again I am choosing the same set of axes x dash y dash and applying the equilibrium condition. So let me first write it along the x axis. Let's see what we get. This is along this plane. Okay, so just let me clarify. This angle is 8 degree. This means this angle should also be 8 degree. Okay. This is also 8 degree. Okay, and this line is parallel to this line. Okay, so there may be some inaccuracy in my drawing, but it's what it is. So sigma fx dash equal to 0. We are going to find out. We are just going to equate the forces along the x dash axis because there is no movement, because the motion is just impending on the critical case. So what I am going to say is that n1 cos 8. Okay. And is there any more force there? Yes, of course. Minus this opposes. Okay. Minus mu n1 sin 8. Okay. Equals n2. This is my equation 3, and I have got it by sigma fx dash is equal to 0. Isn't it very clear? Okay. So let me see what I have to do again. I have to apply equilibrium along the y dash axis. So let's do it. The P force is the force which is cooling the whole system down, and all these forces, these three forces are applying a force along the positive y dash axis. So let me see, mu n1 cos 8 plus n1 sin 8, isn't it, plus mu n2, nothing else, because it is just acting on a plane. So this is again my third equation, which I have obtained by sigma Fy is 0. So let us now evaluate how many variables are there and how many equations are there. So n2, yeah, it's a variable. All these things are known. Mu is known. Okay, mu is given in the question as 0.4. N3 is a variable again. N3, N2, okay, and N1 is a variable, and P is a variable. So in all there are 4 equations and 4 variables which can easily be solved for all the normal action and the force P. Thank you.